In this video, let's practice using our polarity to look at properties. So in this case, here are 4 molecules. Take a moment, put these in order of what you think is the highest boiling. Alright, if you're back, well, they're actually already in that. So let's talk about the amounts. We see that it is, if we look it up, it's 157 degrees Celsius for the boiling point for hexanol. It is 69 degrees Celsius for the boiling point for hexane. It is 36 degrees Celsius for pentane, and it's just about 0 degrees Celsius for butane. Well, let's start down with our smallest molecule on the right. Butane is 4 carbons in size, and as we add more carbons, we see our boiling point goes up. What is happening is we have more nonpolar carbons around to do those interactions. And so the larger our carbon chain gets, the higher we expect our temperature boiling point to be. But as I go from hexane to hexanol, what I find is that it skyrockets much more. Adding extra carbons was adding 30-some degrees Celsius to the boiling point, but adding that OH group, instead of bringing our 70 up to 90-something from hexane to, say, heptane, instead what we see is a jump almost 160. So the increase there of 90-ish, 80-ish, that is much greater. The polar OH group resulted in significantly stronger attractive forces between molecules than an extra carbon worth of nonpolar would have. And so we see an outsized, by comparison to the extra carbons, increase in the boiling point. How big? Well, let's think about it again. What if we have 1,6-hexanediol? In this case, I've added another OH group. What we find is that this one is 250 degrees Celsius. We basically go up about 90-some. Well, that's actually what we saw before. We were nearish 70 and we ended up nearish 160. So about a 90-degree increase, and add another OH group, we see that again. That OH group is increasing it significantly. And this is a common theme. Polar groups, especially nice hydrogen bonding polar groups, add significantly to your boiling point because they have a significant intermolecular attraction. For comparison, let's cut this in half. What if we just have propanol? Propanol has a 98 degrees Celsius. Well, losing that other OH and losing several carbons meant that we had to reduce our temperature quite a bit. And so we actually see that it falls, it's still above even hexane. That OH group is outweighing 3 carbon groups. And so what we see is that even on a short carbon chain, adding that OH group significantly increases our boiling point. If we were to compare propane, what we find is that propane is negative 42 degrees Celsius. I want to take a little further. Ethane is negative 88 degrees Celsius. And so for propane, we're going nearly 140 degrees. That OH group adds almost 140 degrees to our boiling point, where when we did it earlier, it only added about 100, about 90. So why is it so much different on propane to propanol than it was on hexanol to hexanediol? Well, for one, there's just a size limit. Things tend to decrease as you continue to do it. If we look at the jump from ethane to propane, we see that it went up by about 46. Well, propane to butane goes up by 42. Butane to pentane goes up by 36. Pentane to hexane goes up by 33. We get diminishing returns. The more and more and more of something you have, well, compared to the size of the molecule, that new thing doesn't contribute as much. Proportionately, the larger your molecule is, the less it's affected by the new thing that's getting added. And so an OH on a 3-carbon system has a much larger effect than an extra OH on a 6-carbon system. Now, OH still has a lot of effect, as we saw here for our hexanol and hexanediol, but it's not as great as it was for propane to propanol. And so all of these increases, more carbons or more polar groups, do increase your boiling point. But the larger your molecule gets, the more diminished the effect. Well, let's try a few other ones. Let's modify this hexane. So what if we have 6 carbons, but in different shapes? So these are isomers of hexane. They're the same molecular formula, same weight of atoms. They're all hydrocarbons. Take a sec, make a guess. What do you think will have the highest boiling point of these 4? Well, if we actually take a look, what we find is that 2-methylpentane is 62 degrees Celsius. 2,3-dimethylbutane is 53 degrees Celsius. And cyclohexane is 80 degrees Celsius for its boiling point. Why are these so different? They're all the same amount of atoms. They're all nonpolar. Well, this comes down to how nonpolars interact. Remember, if you have a molecule and you want 2 molecules to interact, you need them to be adjacent to each other. So as electrons on one shift around and create temporary dipoles, you have to have nearby surface able to take advantage of that, and they have to be fairly close. These aren't big changes in charge. If you have a rounder molecule, then there's actually very little area that can interact versus the possible area all along a flatter molecule. Think about holding 2 basketballs near each other. They only touch at one small point, but if you have 2 pieces of paper and you lay them on top of each other, they touch all over the whole thing. This surface area interaction is rather significant in allowing your molecules to interact. The larger a straight chain carbon chain is, on average, flatter than one that has subgroups, that has substituents. The more branched you make your molecule, the more groups coming off your main chain, the rounder your shape becomes. As a result, you have less ability to be attracted to your neighboring molecule, and therefore your boiling point goes down. The ring system, however, well, when we draw hexane, we might draw it as a zigzag most of the time, but there's no reason you have to do that. You can draw all sorts of different shapes for it. As a result, it can twist and bend, and it's not always flat. It just, on average, is more flat than the ones with subgroups. A ring, on the other hand, can't really twist around. It's locked in place. You can only bend a ring so far. And so the ring system ends up being flatter on more often than the straight chain. And so it's able to have those interactions more often. If we see this for our pentane, what we'll find is that the boiling point similarly, 28 degrees Celsius and 49 degrees Celsius. This isn't just true for hexane, we see this for all of our branched hydrocarbons. The ring systems tend to be higher than the straight chain is higher than the branched. The more branchings, the lower your boiling point. In terms of boiling point, these are how the carbon chain length and shape versus polar group interact. Just for a little extra, let's look at how it affects solubility. So for hexanol, you can get about 5.9 grams per liter of hexanol to dissolve in water. But for the 1,6 hexanediol, or hexane 1,6-diol, you can get about 500 grams per liter. Because you've changed your proportion so extremely, 6 carbons to 1 OH versus 6 carbons to 2 OHs, which is really a 3-to-1, like you've cut your ratio significantly, which makes your solubility in water much greater. So that diol is significantly more soluble in water. If we were to compare our hexanes, hexane without the OH is 9.5 milligrams per liter. So, a thousandth as much, I guess a 500th as much, but it's significantly less. Without that OH group, almost none will actually dissolve in water. And if it has a nonpolar layer to go to, it will break into that nonpolar layer. If you go to pentane, it's about 40 milligrams per liter. Butane is about 61 milligrams per liter. None of these are very soluble in water, but we actually do see that the less your carbon chain is, the more soluble it is. The idea is that the lower your number of carbons, the harder it is for the nonpolar molecules to hold together, which makes it a little easier for them to just break apart and be dissolved in water. Still, very little does that. And so a little bit of example on how our carbon chain length affects our boiling point, as well as our solubility, and how inclusion of a polar group dramatically alters both of those aspects.